Welcome, friends. In this episode of DEKB7QHC, we're going to investigate Risetime, and this is specific to oscopes and their specifications, generally thought of in terms of bandwidth, but we're going to examine bandwidth and Risetime in one place, and that's on a scope, principally because that's probably the only place that you can measure Risetime without getting into some sophisticated electronics. The scope is quite sophisticated, by the way. Well, let's just cut to the visuals. And here we have we have a pulse. It's going from 0 volts rising to maximum volts. Now this is, as you might observe in the title bar, this is an ideal Risetime curve. And now the specification for Risetime is the time. This is a time scale down here. The time between the 10% mark and the 90% mark of the overall pulse height. So TR is our Risetime. And over here in this inset, this scale down here is linear. This scale over here is log in this direction and log in this direction. So this is a log-log scale. It's showing a bandpass filter presentation, and it shows 3 dB down points right there and there, presuming that this level right here is 0 dB, or our reference point. So this would be frequency 1, this would be frequency 2. Let's see, how have low and high is how I've distinguished them there. Over this frequency range that is well, basically, if we called that mark right there at the tip of the red as 1, and the next one is 10, this is about 0.2 to 2. So we have a bandwidth of, basically 2 in this application. But we don't have any distinct frequencies noted here. That we don't need any of that kind of stuff. That will be determined by the Risetime and its repetition rate. So the lower frequency, the roll-off of the lower frequency is a function of the input coupling. The roll-off of 3 dB at the high frequency is a function of, basically the Risetime. And there is a relationship in that Risetime. I'll pencil it on here. Forgive the odd markings. The pen is appearing invisible. So this is our fundamental bandwidth and Risetime relationship, with a device going into a constant there of 0.35. Okay, I'm going to erase that. Now this is for a perfect, an ideal Risetime. But we're not always provided with that in life. And frequently we will encounter a situation where the rise time is something slower and more rounded as it reaches the top. Again, we're still using the 90% mark, which travels over to this point and drops down to the timeline here to give us this TR, a new TR. So that results in a bandwidth that gives this appearance, a peak at the low frequencies. It descends to the normal corner, high frequency corner, and then rolls off 3 dB. So we've, in effect, we've changed the minus 3 dB of this point, but not this point. So basically, our bandwidth is something, this would be about the 3 dB down point. And we can see that there's it's somewhat wider in bandwidth. Now, if I go to another condition, this, by the way, this, this right here is called undershoot. This undershoot is telling us that the amplifier cannot follow the curve itself and is always lagging. For instance, what was formerly the 90% point over here, now being over here, that's a lag against the actual input. We know this is the actual input. This is what the scope represents. Now we're going to look to what's called the overshoot. In this particular instance, our rise time is climbing faster than the signal, so it's leading it. But it's also causing these little ripples at the top of the top left corner of the pulse, and then vaguely descending in amplitude until it matches the overall peak of the waveform, aside from this little anomaly here. And this is called ringing. So we can see 3 cycles of the ringing. Those frequencies are very related to this response here, this peak at the F high. And again, we're going to be shifting the bandwidth by this, well, it's no longer flat across the top, so we've got a complex geometry that shifts the minus 3 dB point down, not as low as this, but something higher, and it results in a wider bandwidth yet again. So this form of response, this ringing, this overshoot, can be attributed to overcoupling, whereas our previous display is one of undercoupling in tuned circuits. Now, we're not in a strictly tuned amplifier regime here. And let's see, returning to the slow rise time, the fast rise time, and I'm going to show the combination of both of those so that you can observe for yourself. So this is a composite of the first 3 slides. It's showing the actual signal in relationship to a ringing response. So the rise time is kicking an oscillation into gear here. That's how this signal can lead the signal, is that it's stimulating this resonance at this peak that tapers down. Now, you'll notice that this curve is diminishing, so that is called, let's see, well, this is the action of a snubber. A snubber in a switch circuit is something that absorbs these oscillations. And these oscillations frequently come in practical applications. Let me switch here. The slow rise time, the fast rise time with a ringing and such. The ringing part is often found with switches, mechanical switches, like what we find back in this equipment back here, the old style stuff. And those switches we'll talk about later. I'll show you the construction of switches and how this occurs, how we get this ringing. But it occurs at either the top or the bottom, depending upon the state of the switch and what current is flowing. So, returning to this last chart that we had, this also reveals a lot of dynamics that are going on inside the amplifier, and is quickly observed to render in your mind this kind of deviation from the ideal bandpass. So we see that we've peaked the high frequency, done nothing with the low frequency characteristics, and the amplifier rings. Now, this is the principal attribute of an O-scope. You being able to see at one glance how linear your amplifier is. So this is about linear amplifiers, not strictly tuned amplifiers. Also, although they also exhibit bandwidth characteristics. They also exhibit undershoot or overshoot. This particular characteristic, rise time, is a good qualitative examination of your rig. The less ringing, the less droop, so to speak, the undershoot. So bringing that up, bringing down the ringing, getting a flat band pass, all of this, you may wonder, well, so what? What do I lose if I've peaked my high frequency, get a little ringing, life moves on. I have a higher output, perhaps a wider bandwidth. I don't know if that is, I as the operator having this condition, I don't know how much that affects things. However, if we consider not only amplitude, but phase, the rise time is also a function of phase linearity across all frequencies. So you want your phases to be in match at nearly every frequency within the bandwidth. This is something that is very, very necessary in teletype and those modes of communication, digital, because the ringing part is something you don't want to see in your bit stream, especially if it's deep ringing that continues almost forever in regards to a 1-bit waveform. So phase stability, phase linearity is also viewed in the rise time. This is all a quality. It's not. You can correlate the ringing frequencies and the amplitudes and the degradation of that signal to Q in some sense of the ringing part of your circuit. But that's a little advanced for this discussion right now. So I'm going to close it right here and say that rise time is a critical characteristic of your systems, your designs, of the operation of your equipment, something that's easily viewed, but not, you have to have first that very fast rise time signal, and that's not simply achieved. The best way of doing that is using a mechanical switch that is mercury wetted. Mercury, when it pulls apart, it goes from maximum conductivity to zero, just like that. And that's about a picosecond. Tens, maybe hundreds of picoseconds, but certainly far less than a nanosecond. But finding a mercury wetted reed switch would be the perfect, because the reed switch is sealed and mercury is not something you want to have laying around the ham shack. So that's just a hint of the, if you're going to measure a rise time, you have to have something that's rising quickly, and there's very, very, very few generators that come down the pike that don't cost a lot of bucks, that have a rise time that is sufficient to test your equipment back there. So I'm going to close down the topic here. Rise time is important, and I hope that you find something useful in this discussion. So I'll extend my 73s, friends. See you in the next episode.